Hi Year 11, in this video we are going to look at three topics that really kind of don't fit together but are important things that you need to be aware of. We're going to talk first of all about states of matter. I do want to point out this links to physics and particle model within the physics unit, so there is a bit of an overlap. I'm also wanting to do a little bit on polymers. I know I touched on it in the bonding video, but I want to make sure we've covered all the key things around polymers. And then we're going to look at nanoparticles, what they are, and then the types of calculations that generally come up around nanoparticles. So we'll start by, first of all, looking at states of matter. So you can see here I've got my diagram where I have got my three states of matter, and they are in fact changing states, and you have to be able to describe what's going on here in terms of being a solid, a liquid and a gas, and then we need to describe the particles in terms of the force of attraction, whether or not they're moving fast, so they're in fixed positions. So it is important that you do and you are able to describe this. I've seen this come up, believe it or not, as a 6-mark question. So it is important that you are able to do this. So we're going to start off first of all by just labeling the change of state diagram. If you already know this, it is quite straightforward. Then please just power on through, pause it here, give it a go and then check. So you can see I've got a solid here. Okay, so there's my solid, which is then turning into my liquid, which is then turning into a gas. And we'll talk about what causes those processes to occur in a second. But what I do want to be able to do is sort of highlight the key things you need to be writing when it comes to describing a solid, for example. So we'll start off by drawing a picture. So here is my solid particle diagram. Key things that we need to know about solids is that there's basically a strong force of attraction between the particles. That's what keeps them together. Okay, the particles are touching. Essentially, they're close together in what we call fixed positions. Okay, and we know this type of structure is what we call a regular lattice type structure. Okay, so we need to think about the force of attraction. So there's a strong force of attraction. That's what keeps the particles together. The particles are close together in fixed positions. We know that particles are continually moving, even as a solid, but they are essentially vibrating in these fixed positions. Okay, so we're going to say particles vibrate around fixed positions. And as you make them hotter, which you will be if you are, for example, melting them into a liquid, then these will essentially vibrate more because we're providing the particles with more energy, which is kind of getting into physics territory. So you need to be able to describe the particle model of a solid. That's the key things. Oh, there's one more thing actually. We need to remember that it keeps a definite shape and volume. Okay, so just be aware that it keeps a definite shape and also a volume. Next one is a liquid. So if this was a 6-marker, I'd be drawing the diagrams on there just to help keep me right. So here is my liquid. Okay, not very good at drawing, as you can see. So between a solid and a liquid, there is a weaker force of attraction. because, as you can hopefully see from my diagram, they're no longer in this lattice structure. In fact, they are randomly arranged, and they move past each other quite a lot. So they almost like roll over each other. So they move past each other. But as you can hopefully see from the diagram, they're still close together. So they're still touching, so they can move past each other. It also has a definite volume. And can take the shape of a container. So if I pour water into a beaker, then the water takes the shape of the beaker. So that's the important thing we need to remember about a difference between a liquid and a solid. Solids don't do that because they've got a definitive shape, whereas liquids take the shape of the container, but they have a definitive volume. The particles are constantly moving. And as I said already, they move over each other, but this process is random. Okay, so they move over each other, but it's random. And again, hotter equals faster movements, which can eventually lead to, obviously, expansion. But essentially, that's the key things that we need to know around a liquid. So they've got a weaker force of attraction than a solid. They're randomly arranged, and the particles can move past each other, but they're still touching. They have a definite volume, but they take the shape of whatever container they are in. Their particles are constantly moving, and this movement is random. And when you heat the particles up, it makes them move faster. So the final one I'm going to draw at the top here, just because I'm running out of room, is a gas. So we can see that obviously the force of attraction here will be weaker. And we know that because the particles are far apart. Okay, they're moving randomly. There's no fixed pattern to it. They do not keep a definite volume or shape. And they always, this is the one we always forget about, but they always take the shape of the container. So if I have, for example, air in my beaker, which I would have because it's sitting out, it's going to take the shape of the beaker. Same as before, you heat up the particles, they will move faster. So they do, in fact, have a greater kinetic energy than that of a solid, and that's why they can move a lot faster. Okay, so like I said, that can be a 6 marker. You just need to know about each state and what the key things are. But now what we're going to look at is a change of state and how what processes occur, and then how to spot that, for example, on a graph. So we've got a solid turning into a liquid, so that is obviously melting. So I require energy to do that, to overcome these forces, make the particles move faster. From a liquid into a gas, we would evaporate, but we'd call that boiling. Okay, so a liquid turning into a gas. A gas turning into a liquid is condensation. That's the process that takes place. And then from a liquid into a solid is freezing. Now, as I said, this could come up as a graph, and you need to be able to spot when we have a change of state taking place within a graph. So here I've given you a change of state graph, a typical one. I've actually used this recently in physics. So what I want you to essentially see is the flat lines, and the flat lines are telling me that there is where a change of state is taking place. Okay, so we can imagine that if I start with a substance that is a solid, and as you can see, the temperature is going up, the particles are vibrating, and as a result of that, they are producing So here is my solid, which is turning into a liquid. And in order to do that, those particles have to gain energy. So the particles gain energy, which obviously weakens the force of attraction between the particles. And once it has enough energy, it will break free and become a liquid, in other words. So what we're looking for is a flat line. Okay, so the flat line shows the change of state. So just be aware of that. Obviously, to turn from a liquid into a gas, I'm going to need even more energy than before, which is why the temperature is higher. But the process is the same. The particles are gaining energy. We're weakening the force of attraction until they have enough energy to break free and turn into a gas. Now, types of questions you generally get around this are usually data questions where you've got a table and you might be given, for example, oxygen, nitrogen and bromine, and they give you the melting point and the boiling point of the substances, and they might say to you, which of the above is a liquid at room temperature, and then give you the room temperature liquid at room temp. So room temperature is around about 25 degrees Celsius. So the melting point of oxygen is minus 219. The boiling point is minus 183. Minus 210, minus 196, minus 7, and 59. So you're essentially wanting to know that melting means it's going from a solid into a liquid, and boiling means it's going from a liquid into a gas. So we are sitting here at 25 degrees Celsius. So oxygen would have melted and also boiled at that temperature. So that would be a gas. Okay. Nitrogen would also be a gas at that temperature, whereas bromine would have in fact melted into a liquid but would not yet be a gas. So I can tell that bromine would be the one that is the liquid at room temperature. So they are the kind of questions you get around it. You might get a graph question. I'm not seeing that very often, but it is important that you're aware of where change of states take place. State symbols, I mean, we've done these already. Solid, liquid, gas, and AQ are your 4 state symbols you need to know. So solid, liquid, gas, and aqueous, which means it is dissolved in solution. Okay, and you need to spot these in equations, and you might be asked to tell you what it is. I've seen that in the foundation to your question. Key is reading the question. Okay, so that's the changes of state. We're now going to look at polymers. I wanted to add in polymers only because I know we talked about it in the bonding video. I just felt we needed a little bit more context around polymers just so I feel confident we know what they are. So the word poly means many. Okay, so polymers are many what we call monomers joined together. Okay, and so mono means one. So it's one thing that we then join together to make this big long chain. Well, it can be a hydrocarbon. So what do you need to know about polymers? You need to be able to spot a polymer from the picture. So what you'll always see from a polymer is you'll see the bracket. You'll see this thing here, which is the scientific term or even the maths term for many. So many of, lots of. What we're saying is we've actually got lots of these units all joined together. You can see the line comes out beyond the bracket to show you that in fact we've got this long repeating chain. Polymers are covalent molecules because they're generally non-metals. So remember, covalent is the bonding of non-metals. So you can see I've got carbon and hydrogen, they're non-metals. And as I said already, these are lots of small units that are linked together to form this long chain. Okay. So for example, here you can see I've got my long chain. That there is the abbreviated version of this. Can you see how I've got this repeating unit throughout, which tells me actually this would have been made from an alkene, which would have been ethene, which is paper 2 stuff, guys. So don't need to worry about this for paper 1. But essentially, the alkene would have broke the bonds and then allowed it to join lots of these repeating units together to form this big long chain, which is our polymer. So a couple of things you need to know about them is that most polymers are solids at room temperature. So you might get a data question on it. So just bear in mind they're solids at room temperature. The intermolecular forces between polymer molecules are larger than that of simple covalent molecules. So if I had to put the forces in order, I'd put polymers above simple covalent. So polymers have a stronger intermolecular force compared to simple covalent molecules. And we'd expect that because simple covalent molecules are usually gases at room temperature. And we know that these guys are usually solid, so we'd expect that to be stronger than that of simple covalent. What I do want to point out though is that these are weaker than ionic or giant covalent structures. So just be aware that they therefore will have a lower boiling point compared to those two structures. So again, if you were given a table set of data and it said solid at room temperature has a boiling point of, I don't know, 27 degrees, then you would know that it's got a lower boiling point than any structure that is ionic or giant covalent. Okay, I can also write this as a formula. So you can see I've got 2 carbons there, so C2, I've got 4 hydrogens, 4, and because it's repeating units, I'm going to put an N there to show that it means many of. So exam questions I've seen data questions on this. I've seen them asking you to tell them what that there means. So it means many of these things joined together in one big long chain. I've seen them ask about the type of bonding that it is, so you need to know that it's covalent. But essentially, that is the little add-on that I wanted to do because I just felt we didn't do enough depth on it in the bonding booklet. So the final thing we're going to look at in this video is our nanoparticles. So we're going to talk about what nano means. We're going to talk about the types of questions you get around this, how we use nanoparticles, and you may, for example, be asked to evaluate nanoparticles in terms of their use. So it's important we're aware of the types of questions that come up on this. So the word nano, I've seen them asking them to define it. It means really, really tiny. Okay, so they're really tiny particles. It's not enough to say small. So just be aware, you need to say the word tiny. Because they actually have a diameter that is exceptionally small. Okay, so they have a diameter between, 1 nanometer is like 1 times 10 to the minus 7 meters, so exceptionally small. And they can go even smaller than that, bigger than that, where they can actually go up to this size, which is 2.5 times 10 to the negative 6 meters. So they're exceptionally tiny molecules. Okay, and because they're tiny, they're used for a variety of different things. So we're going to look at the uses of nanoparticles. So the first use I want you to be aware of is that they're all often used as catalysts in industry. So catalysts, speed up reactions. So we can use nanoparticles to help speed up reactions. We also use them in nanomedicine. And this is where a lot of the forefront around cancer research is actually looking at, where we might want, for example, a treatment to be absorbed into the blood. Nanoparticles are very easily absorbed by the body. So we're going to say that, absorbed by the body. And they can then go into the body and move around in the blood because they are tiny. And essentially they can deliver drugs to tumours, for example, rather than destroying the body tissue. So because they're small, they can be absorbed into the body very easily, and they can be used to transport drugs to specifically target types of diseases that might be needed to be targeted. We also use nanoparticles in electronics, because nanoparticles do in fact conduct electricity, or they can. So we do use them for that. So circuits, for example, we can use them there. We give you a specific example of nanoparticles, which is silver nanoparticles. And you need to know that they have what's called antibacterial properties. So in other words, they're used to kill bacteria. We can also use them for polymer fibers, really strong molecules. They're also used nowadays in cosmetics. And I've even seen them used, well, they are used in sun cream. And as I've already said, you might be given a table of like pros and cons for each of these specific types of things, and you might therefore be asked to evaluate the use of nanoparticles. The key thing really is that we do not fully understand the health effects that these types of particles can have on the human body. So it's not fully understood in terms of the long-term impact in terms of health effects. So even though they're great for use in a variety of different ways, we don't fully understand them in terms of long-term health effects. So it could be a table question, could be a 6-marker where they give you lots of data around a specific type of nanoparticle that you've maybe never heard of, but the skill they're assessing is, can you look at the pros and the cons and come up with a conclusion about why you would use them or not use them. But it's just to be aware that they are used in a variety of different ways. The final thing that you need to know about nanoparticles that does come up quite a lot is it's used in calculations. And you need to know about nanoparticles in terms of surface area, because they have what's called a high surface area to volume ratio. And you might get asked to calculate the surface area of a substance, the volume of a substance, and then calculate the surface area to volume ratio. So you can see from the diagram, nanoparticles react more quickly because they've got a high surface area to volume ratio. So we need to be able to calculate surface area to volume ratio, and you need to know this calculation. This is where your maths comes in, because I know you do this in maths. So surface area to volume ratio is essentially the surface area divided by the volume. And we'll go through some examples of this on the next page. So you can see it's often a cube. It's usually a shape that you should be pretty familiar with. So this is all math skills. In fact, having marked quite a lot now of papers, especially here, we're very good at this. So it's very much assessing your math skills here. So you've got a cube. It tells you the dimensions of the cube, and it's asking us to calculate the surface area for one face. So I'm looking at one face here. I can see that we've got 20 along here, which I'm going to there times by 20, and that's going to give me my surface area of one side of the cube, which in this case is 400. I've then got to do the total surface area of all 6 faces. So I've already worked out what one side equals. So we know that a cube has 6 faces. Now, I do want to point out, higher tier, you've got to just know that. Foundation tier, you might get a scaffold. It just depends. So 400 times by 6 gives me a total surface area of 2,400. The volume, we also need to take into account the depth. So we've got 20 times by 20 times by 20. And that equals 8,000. And then I'm asked to do the surface area to volume ratio. So I take my surface area number, which is 2,400, and I'm dividing it by the total volume. And that's going to give me a ratio of something to 1. So let's see. So 2,400 divided by 8,000 gives me a 0.3 to 1 ratio. Okay, so just be aware, you're asked lots of questions on this. It's usually a sort of 4-marker question, but hopefully you found that video useful. It's given you a little bit more information about states of matter, polymers and nanoparticles. But as always, if you've got any questions, don't hesitate to ask. All right, thank you.